another example that we touched on last class. I told you it's possible to switch between continuous growth models and discrete growth models. For example, if you have this equation right here, v equals a times e to the rt, you're assuming continuous growth. You're assuming that v is growing continuously at r% per instant. Okay, it's growing continuously. Actually, the interest rate would be per year, but it's growing instantaneously. Okay, at that rate per year. In a discrete model, the form is a times 1 plus I raised to the t power, where I is the annually compounded interest rate. So, for any given annually compounded interest rate, you can find the equivalent continuously compounded interest rate, and vice versa. For any given value of r, you can find the equivalent value of I. Suppose you want to solve for the continuously compounded interest rate that's equivalent to a given value of I. Then what you would do is you would take this equation right here. You want them both to have the same value of v, both to have the same future value. Divide both sides of this by a, and you get e to the rt equals 1 plus I raised to the t power. Now, take both sides of that equation and raise it to the 1 over t power. Doing that, you get e to the r equals 1 plus I. So I, the annually compounded interest rate, is just e to the r minus 1. Suppose, I forgot. We were doing r first, assuming you knew I. If you knew I, we don't have to do this, excuse me. If you already know I, this is good enough. Only, see, our goal is to solve for r. So if we know I, how are we going to solve this equation for r? Heather? Take the natural log of both sides. And taking the natural log of both sides, we get the natural log of e to the r power equals the natural log of 1 plus I. And one more thing, Heather. What is the natural log of e to the r? That's just r. Because you could use rule number 3 to bring this exponent down and write this as r times the natural log of e equals the natural log of 1 plus I. And the natural log of e is what? 1. So it's just r star equals the natural log of 1 plus I. Okay. So if I give you the value of I, you can solve for the equivalent value of r. For example, suppose the annually compounded interest rate is 0.09. What will be the equivalent continuously compounded interest rate? Well, it would be r star. What is the natural log of 1.09? Anybody? Heather? 0. 0.0862. That's good enough. So in other words, there's not a great difference between the two. As long as the interest rates aren't too high, the difference between the two will be relatively small. And it does make sense that the continuously compounded interest rate is always going to be lower than the continuously compounded, than the annually compounded interest rate. Why is that? Assuming that the annually compounded interest rate is positive, why is the continuously compounded interest rate going to be always slightly lower? Why does that make sense? Yes. Right. Yes. Exactly. Yes. If the rates were the same, but it was compounded continuously, you would end up with more money. So the continuously compounded interest rate is always going to be slightly less than the annually compounded interest rate. Here the annually compounded interest rate was 0.09, so it makes sense that the continuously compounded interest rate would be slightly lower. Now the bigger the interest rates get, the bigger the difference between the two. But if interest rates are relatively small, then the difference between the two won't be that great. Okay. Great. So this means it's possible by using logarithms to switch back and forth between discrete growth models and continuous growth models. Okay. Now, let's go the other way. Suppose the R value was 0.06. What would the equivalent I value be? Then we would want to solve for I. R would be known. So in this case, it would be very easy. I star, taking this formula right here, would just be e to the r minus 1. Okay. And if we assume that r is 0.06, then I star is just e to the 0.06 minus 1. So what would this be? E raised to the 0.06 minus 1 is what? John? Okay, 0.06. What's 1/8? Okay, that's far enough. Okay. So again, it makes sense, doesn't it, Sean, that the annually compounded interest rate is slightly higher than the continuously compounded interest rate. You need a slightly higher annually compounded interest rate to compensate for the fact that you're only compounding once a year instead of continuously. Okay.